In this video, we will discuss about phase transformations. So let us look at what exactly is a phase transformation. So let us draw the liquid here and then the gas here, then the solid here, then this is another solid. This liquid is converted to the gaseous phase through a process called evaporation. This is a phase transformation, liquid, gas, and solid, and this is dash that is a different type of solid that are the different phases. And this gas can be converted to liquid through a process called condensation. Process called condensation. And this liquid is converted to solid through a process called freezing. And this solid is converted to liquid used in a process called melting. Okay, so liquid can be converted to solid through freezing, and solid can be converted to liquid through melting. And this solid can be directly converted to gas using a process called sublimation. Process called sublimation. A process called sublimation. And this gas can be converted to solid directly using a process called deposition. Okay, that is why how the dry ice that is CO2, etc. is formed, dry CO2. And and this solid can be converted to another phase that we have seen that in phase diagram, particularly in iron carbon phase diagram, how this austenite is converted to alpha and cementite. Okay, so this phase transformation, that is from one solid phase to another solid phase, this is called solid state transformation. This can be achieved, the solid state transformation. This can be achieved using the process called the heat treatment. Okay, heat treatment, right? So these are the different phase transformation process. So our focus will be on this heat treatment process. How can you change one phase to another phase? That is very important in terms of the uh, is how to control. You can by this heat treatment process you can control the properties of this material. That is very important for the metallurgical activities. Okay. Now let us understand. Try to understand the phase transformations from solid from this gaseous liquid state to solid state. Phase transformation, liquid state to solid state. So we have seen that when the liquid metal is cooled. Okay. So first let us see here. The liquid metal is cooled. Initially it was all okay, liquid, and when it is cooled, what we get, new solid crystals will start to form. New solid crystals will start to form. Uh, that will be, okay, you can find this here. Uh, so you can see that there will be formation of liquid crystals. It starts to form uh, in some regions. Okay, that liquid is getting converted to solid. So what happens as time passes by? When it is cooled further or when the temperature is decreased further, you can see that this solid crystal gradually will gain size. Okay, its radius will be increased. At the same time, some other nucleus will also start to form. Okay, along with the growth of the these existing crystals, solid crystals, another nucleus will start to form. So that means in another step, its radius increases, and also the radius here will increase, and a new crystal may form. Okay, and a new crystal will form here. Um, so here, okay. New crystal will form. Again, after some time, this crystal will gain size. You can see that this crystal will gain size. Okay. You can see that existing crystal will gradually grow, and also mm, new crystals will form. So this is what happens. Right? New crystals will form somewhere here. So this is how the crystals form as time passes by. So that means we will take two points here. That is, first one is the nucleation rate. So that I is the number of nucleation events. That means the new crystals forming per unit volume per second. Okay, per second. That is I. And also you have this growth rate. Okay, growth rate. This I is called nucleation rate. I is called nucleation rate, and G is the growth rate, or you can write it as dr by dt, or so that is defined as the rate of increase of the size of particle, rate of increase of the size of particle. That means this R is the particle size. We have seen that the existing crystals gradually, the radius of the existing crystal gradually increases. Okay, so that means the overall transformation rate, overall transformation rate, the overall transformation rate is given by dx by dt. That means the transformation from this liquid to solid. See, x is the fraction transformed. This is the fraction. This is a function of this growth rate and the nucleation rate. It is the function of growth rate and nucleation rate. So that means if you draw a graph, you can see that this is x and this is transformation rate. So this graph will appear like this. So that means initially the transformation rate, you can see that the transformation rate as time passes, initially it was slow, gradually it increases and then it slows down. Okay. So initially this is slow due to because the less number of nuclear forms. The nucleation will be slow initially. Okay. After finally it will slow down here in this region. It will slow down. Now let us see the temperature dependence of temperature dependence of I, G, and dx by d. So, so let me draw a graph here. So this is So this corresponds to this y-axis corresponds to temperature and x-axis corresponds to uh, that is it is I, G and dx by dt. So let me draw that. So this curve corresponds to growth rate and this curve corresponds to this depletion rate and this curve corresponds to the dx by dt. Okay, let us see why this happens. For that, first let me draw some flow. This is dg max. Okay, and this one is di max. Di. You can see that when this liquid is transformed to solid, so that means you are cooling it. So what happens when you are cooling it? This is, see, this point is the melting point. Okay, this is the melting temperature. Okay, when the temperature is reduced, you can see that this G suddenly increases. You can see that graph here. See, this G, okay, G increases. That means, so in the x-axis, it shows the increase. That means the growth increases. Okay, here up to here, the growth will be maximum. Okay, that means the existing crystals will gain its size. Its radius will gradually increase. But if you look at that, if you reduce its temperature, that means let us reach this temperature here. You can see that the new nucleation events will increase at this temperature. That means at a temperature considerably lower than the melting point. That means at this temperature, these nucleation events, that is, new nucleus, starts to form. But in this case, the growth rate is low. And here, the nucleations were low. Okay. So that means the transformation depends upon both growth and the nucleation events. So that means transformation will be, so here Tx max, transformation will be high somewhere in the middle. Okay, so important point that you need to keep understand is that when the temperature is high, this growth rate is high and this nucleation events is low. Okay, and temperature is low. Okay, this growth rate will come down and nucleation rate will increase. So this idea, this knowledge, okay, is the basis of heat treatment process. Okay, heat treatment, because by controlling the temperature you can have different structures. We will see why we will get a different structure. Okay, okay, so this is the basis of transformation. That means the transformation depends upon this, overall transformation depends upon the growth rate and the nucleation. Okay, it depends upon these two factors. So based upon this, we will draw a TTT diagram, or better called time temperature transformation diagram. Time temperature transformation diagram, or you can write this as TTT diagram. So this is the basis of all the heat treatment process. We will use this TTT diagram for the in combined with FEC phase diagram, that is iron carbon phase diagram, to get different types of steel, to get different microstructures of steel. So, so let us draw the TTT diagram. So in the y-axis you have this temperature, x-axis you have the time. Okay, so it's melting point here. This is the T melting point. So, see, so when it is cooled, so this axis corresponds to temperature. So when it is cooled below this melting point, you know that this liquid is getting converted to solid. It is gradually, melts. See, this is not the melting point. So this is the transformation temperature. Just understand like that. So, so what happens when it is cooled down? You know that when it is cooled, is gradually new crystals will form. That is the nucleation events. That is I. There are new crystals will form, and the crystals will gradually gain in size along with new nucleation events. So we have already seen that this when the temperature is high, the growth rate is high, and nucleation events is low. Okay, so that means I take a particular temperature here. So at this, so the transformation starts here. Here, that means the liquid to solid transformation starts here and it ends somewhere here. Okay, that means after this point, so I time as time passes by, it is completely converted to solid. So when it is see, again, if I for a particular temperature here, if you look here, you can see that the transformation starts here at this for this particular time, and then the transformation ends here. Okay. So when I reaches this temperature here, the transformation starts here because see I told you the see somewhere here this dx by dt is maximum at somewhat the middle temperature. Okay. So as I temperature further decreases, transformation starts here and it ends different here. A transformation ends here, right? And then see, as I go further down, you can see the transformation, see, occurs. It is not so fast. The transformation is not so fast. So the transformation starts only at this time, and then you can see that the transformation ends here. Okay, then if you go further down, I mean, if you further down, you can see that the transformation starts here and it ends here. So if you connect these curves, you will get a C curve. Okay, so you will get C curve. So these are called C curves, and this is the uh, time starting time. Okay, and this will give you the end time of the transformation. So that means if you draw see, for this particular temperature, okay, this is what particular temperature, the transformation starts here. T start is it is the start and here the T stop. Here it is T stop. And temperature starts here and stops there. So you can easily find at what time starts corresponding to a particular temperature. So that is why this is called a TTT diagram. Okay. So now let us see. Okay. Now let us try to cool a liquid from here. So that means okay, let us take this line, right? Right. See, suppose uh, I have a liquid here. So here you have a liquid. It is slowed cooling. Slowed cooling. That is, you're slowly cooling it. If it is slowed, and you can have a fast cooling also. For example, like this. Okay, this is fast cooling. Okay, this is fast cooling, somewhat fast cooling. I can have much more faster cooling. So let us see the microstructure evolution in these two cases. That is slowed cooling and fast cooling. Okay. That is in slow cooling. Slow cooling. So you can see that here the transformation happens at a higher temperature. This transformation happens at a strong high temperature and transformation stops at a lower temperature. Here you can see that the transformation happens at a somewhat lower temperature and also the transformation stops at a somewhat lower temperature. Okay. So that means what happens when the transformation is at a higher temperature? What happens to the microstructure change? If we look at the microstructure, I have told you that at higher temperature, there will be, so if you look at the previous figure, at higher temperature, growth rate is high and nucleation is low. At a lower temperature, growth rate is low and nucleation is high. So that means at a higher temperature or the slow cooling, you will get a coarse grain like this. That means, so this is where the new nucleation starts. Okay, the nucleation will start gaining its size. Okay, that's all. Nucleation will start gaining in size. The new nucleation events will be slow. And it is for, if you look at the faster cooling, if you look at the faster cooling, you can see that new nucleation events. Okay, so it since it is transformation occurs at a lower temperature, new nucleation events will occur. So that means you will get a lower temperature. Okay, so that means you will get a fine grain. Okay, this is how you control the microstructure. This is how you control the microstructure. Slow cooling means transformation occurs at a high temperature. Occurs at a high temperature. In high temperature, the growth is high and nucleation event is low. And then see here, the transformation occurs at a lower temperature, and here the growth rate is low and the nucleation events is high. That's why you will get a finer grains with more nucleus. So now let us look at another process here. So let us look at another process here. So what if the transformation is very fast? So you can see that it did not touch any of these circles. That means the transformation didn't even start. The transformation didn't even start. So, and this type of cooling is called very fast cooling, or very fast cooling, and this is given a name, quenching. This is given a name, quenching. That means here the transformation to solid is suppressed. Is suppressed. So you will get a undercooled liquid. Undercooled liquid. So as temperature is this is okay, fine. You will get an undercooled liquid. This is called quenching. So this is the dependence of temperature and time and transformation. Earlier we have seen in phase diagrams we did not include time. Okay, so time is also an important factor. How fast the cooling occurs. Okay, earlier we had given infinite time for the transformation to occur in the phase diagrams. Now we will consider the parameter that is the time also.